All right. Well, today I want to talk about something entirely different. Let me get share screen going here. I want to talk about inverse kinematics. Now, first of all, there's an inverse kinematic system that works with the mechanism system, but it's designed only for humanoid, and it actually says properly constructed humanoid characters. I don't know what that means. But I want to talk kind of about a more general version of inverse kinematics. The basic idea behind IK is that you're going to calculate the positions and angles for a joint system so that the end of the joint system reaches a certain goal. There are a lot of different algorithms for inverse kinematics, and I'm going to focus on one called FastIK, forward and backward reaching inverse kinematics, because it's really quite easy and fairly efficient. Before I dive into inverse kinematics, let me first define forward kinematics. If we have a starting point and we have various lengths and angles that define the relationship between these, it's fairly straightforward to calculate where the end point is. That would be forward kinematics. You define the lengths and the angles, and your end point is defined by the geometry. With inverse kinematics, it's knowing where we want the end of our chain to be. And inverse kinematics will find a configuration for the joint system that will reach that position from the origin. So we don't know the angles. We do know the lengths. Those are kind of fixed, but we don't know the angles. And we have a goal, and what angles will produce a configuration that reaches that goal. FastIK is relatively low cost. I'll show you some extensive stress tests of this. And it's low cost because it's a heuristic, as are most inverse kinematic solutions, meaning that they're practical methods that don't necessarily yield either the perfect answer nor the most optimal answer, but it will find one that's a pretty good guess. And the concept behind FastIK relies on an iterative process where we start off with a position of joints, we make some adjustment to it, and we repeat this iterative process until it is good enough. So here's our situation. We have these different points, 1, 2, 3, 4. We have the lengths, 1, 2, 3, and we have some target that we want to reach. And we don't actually have to define both the points and the lengths. If we just define the points, of course, we can extract the lengths by the difference between 2 points. One trivial solution that we encounter is the case where the target is not reachable. And this would be the case where the sum of the lengths of the members is less than the distance between P1, which, by the way, is fixed, and the target, in which case we just line them up in a row and extending from P1 pointing towards the target, which we fail to reach. FastIK is, as I mentioned, is iterative, and stages. Sorry about that. A little flicker there. Each of these, each iteration has 2 stages. The first stage takes a best guess as to where each joint should be by first setting the last position of our chain to be at the target, and then working backwards to the beginning. This process of working backwards is done by finding the line between the most recently updated point and the next point backwards, and moving along that line by the distance between those 2 points. I'll show you a picture in a minute. And in fact, here's the picture. So moving 1 point, we move P3 towards the target, this length D3. And that moves P4 over here. And then we repeat this process going backwards down the chain. We now move P2 over to here, which is now D2 from P3, and we move P1, which is now D1 from P2. We end up with a gap here between the start and our new calculated position. The second stage is essentially the same operation, but this time we're going to do it by setting that P1 prime back to its origin, and then moving forward through the chain, adjusting each of these lengths. And once again, when we're done, we have some gap here. But if you look back to what we originally started with, the gap is much smaller. So that one iteration has moved us to a configuration that is closer to the target. And we repeat this iterative process until it's good enough. Now, there are a couple of ways of doing this. Of course, we expect some error. We can just specify a tolerance. When it gets within a certain closeness, we're good. But also, since these heuristic methods can fail, it's good to have some maximum number allowed in case it can't find a stable solution. So code courtesy of D.E. Ditzel. This is his GitHub page where it comes from. I've modified it somewhat, but basically we have the chain length, we have a target. I'll talk about the pole later. We have an accuracy delta that we want. We have a snapback strength that will appear, and we have various arrays to hold the different components of our model. In start, I'm going to call a function init, and the reason that I'm encapsulating this is that at some point later in the code, we may need to reinitialize things. For instance, if the number of elements, or bones as we'll call them, changes. So this just exposes this so that we can call it another place. So what we do in init, of course, is allocate all the different arrays. The bones are transforms that contain positions and rotations. The bone length, the floats that are how long they are, the D's in our previous picture. Start direction, that's a vector, and start rotation of the bones that are quaternions. And the positions, these are the things that we're going to be modifying. Continuing with init, we set up the bones. We kind of start with the leaf, the bottommost node on our chain of elements. This is also the part of the arm that has this script on it. And we're counting down from the bone length, -1, down to 0, and decrementing I. This is a countdown loop. So bone I is the current one. We catch the rotation, we catch the direction between it and the target. If we're that leaf, if we're not the leaf, we catch the its position minus the current position and get its length. And at the same time, we're accumulating here the total length of our chain. This will come into that case I mentioned where we can't reach it. And at the end of this loop, we go to the parent of our current leaf, of our current member of the chain. We've got an error trap for bone 0 being null. This would occur if the chain value, the requested value was larger than we had actually provided members of our chain. And here is also something that allows us to put the object in a container object, which we might want to do. If the parent of bone 0 is not null, then we catch bone 0's parent's rotation. Otherwise, we use identity. Now, similar to what we did in start, in late update, I'm going to call resolve IK. This is the thing that does the calculation. And again, I'm doing this in case we need to invoke this elsewhere. We have a bailout if there's no target. We initialize if the chain length has changed or doesn't match the bone length. And then we catch all of the bone's positions into the positions array. We catch the root rotation in case the root is not part of the chain. And root rot diff will appear later. This is the product of two quaternions representing rotations. And from the science of quaternions, a product of two quaternions is also a quaternion, so it's also a rotation. Our first test is to see if it's possible to reach the target. So if target position minus the bone 0 position's square magnitude is greater than the complete length squared, then we just stretch the chain of objects out in the direction of the target. So this direction is target position minus position 0. We normalize it to get a unit vector, and then we place we position our bones in the direction scaled by the individual bone lengths. So that's the trivial solution. Now, in the case that we can reach it, the first thing we do is snap back the positions using that root rot diff rotation that we found earlier, times the original start direction. A quaternion times a vector yields a rotated vector. So we're kind of rotating things back to their original position here before we start with the iteration. And now we start the iterations. And we have the backwards, this should say back here, B-A-C-K. We have the backwards iteration where I set position length minus 1 to the target position, and then I form a direction between link I plus 1 and link I, normalize it, and again move the next position in that direction along that bone length. So this sets the line on that distance. The forward stage is quite similar. We're now looping forward, ignoring this first one. So instead of I equals 0, we start at I equal 1. We form a direction and we place our bones along that direction as we step up the chain. Notice there's a minus here, and in this case there was a plus here. That's the difference between those two. And then we can test to see if we're close enough, forming a distance between our final link's position and the target position, getting the square magnitude of that and comparing that with our delta squared, which is our accuracy. And that's all there is to that. The optional pole is a position in space towards which we will drag the chain. So the chain, instead of being kind of planar and straight, pointing towards the object, is dragged off in a direction towards this pole. And I won't go through the arithmetic of this, it's somewhat complex. Finally, there's an on-draw gizmos. This draws little green boxes in the scene view, and in the game view, if you have gizmos turns on, that kind of shows you the shape of the different bones of your object, and it's just for debugging purposes. So that was not insignificant coding, but it's pretty straightforward, and for a heuristic algorithm to do a complex problem like inverse kinematics, it's relatively straightforward. Let me show you an example here of a little robot arm here, down here at the bottom. So here's a little robot arm. I've got a target here that I can move with the Z and the A keys, and I can move it in X and Z and up and down. And if I move it way over here, it's out of reach, so it's put this thing on straight. But this is a little robot arm operating as we would like. So I got tired of setting up robot arms by hand. So I wrote an arm generator script that I won't bother to go through. But the arm generator specifies the number of links that I want to have, whether they're to be all the same length, that's the linear case, or to have them graded from a minimum to a maximum length. This is the progressive min-max, as well as having the arms taper down as they go from the root out to the leaf, or taper the other direction, tapering to be narrower at the root. So here's, these were statically set up. I positioned each of these generators by hand. And this is, I think there's 16 of these here. It's a little square. The object, I can turn off the auto movement, reset it back to the center, and move it by hand with the ZA, SX, and VC keys. I'll let you play with these other ones, but here's a circle of a whole bunch of them. What I did here was I actually got tired of setting up the generators manually, so I wrote a generator script that is capable of laying out squares, circles, and spheres of prefab arm generators, all with the same target. And so these are kind of short ones that don't reach. Here's one that has longer ones. And again, I can move things around manually. And when I get out of reach, they just all make straight lines. And I believe here's a square generator. And here is a sphere generator, which makes a rather odd structure whose utility I have no idea, but it certainly looks kind of cool. So it occurred to me that these things look kind of arachnid-like. They look like crabs or spiders. And so if I added a leg manager script onto the target object that systematically moves the base of the chains so that it looks like it's walking along with the target, making sort of a spider. And here's my best sort of spider here. I can move the body of the spider up and down, and I can make it walk to the left and to the right. And it moves its legs here, in this case, in a specified order, but you can also ask for a random order. Can crab sideways as well. So, and there are various other spiders here. Also, I have transparent links that make kind of weird looking structures. Again, I have no idea what you'd use these for. In the static case, with this thing turned off and these things set, it's certainly making a building structure that would look pretty cool in the scene. And of course, it's not taking any cycles when it's fixed. So this could be pretty cool. So that's inverse kinematics for animating a robot arm. And I'm going to stop sharing and I'm going to end the recording and I'll see you all in class. Bye.